I think I figured it out, but I'm not sure.
All right, so what you got?
I got, find a polynomial with integer coefficients that satisfy the given conditions. Polynomial Q has 3 degrees, 0 is -5, and 1 is plus I.
Important part, you spell out zeros were.
-5 and 1 plus I.
All right, guys, so if I have a third degree polynomial, I like it. That's what it would look like. So they said the name of the polynomial was Q. What the hell? So whatever this thing is, x cubed, some blah, blah, blah. If it's third degree, at the end, I should be able to have how many of these?
3.
3. Which means I should have how many zeros?
3.
3. So what's wrong with the list of zeros they gave me?
There's 3.
There's 2 with an understood third one. What must be the third one? I like it. So they didn't tell you this because you should just know it's there. So if it's got a 1 plus I, 0, it has to have a 1 minus I. Because part of the things that it has to have integer coefficients. We saw some of those, we did some yesterday with i's as coefficients. And then all bets are off. The answers can be whatever the hell I want to be. But when it has integer coefficients, when q of x is 7x cubed plus 5x squared, the numbers in front can only be integers. Then the zeros have to have, any complex numbers, their conjugates have to show up too, so that they'll kill each other when you multiply them out, right?
That's what I couldn't figure out.
Okay.
I remember you talking about it, and then I actually looked in the book right before class and went, I'm a dummy.
Now how do I write this, based off of what we just said?
X plus 5, and then x minus 1 plus I, and then x minus 1 minus I.
Cool. Alright, now you multiply all that stuff out.
Is there a trick to doing that fast?
This little piece here,
Yeah.
this is a square, difference of squares, right? This would be x squared minus 1 plus ix, minus 1 minus ix, minus 1 minus I squared, which is 1 plus 1, which is 2. Let me do that again. This times this. So is it cool? I'm just foiling this thing out.
Yeah.
Just slapping these things together without even thinking about it. But then the last one is 1 plus I, 1 minus I. That's a difference of squares kind of thing. Right? So 1 plus 1 is 1. I times negative I is negative I squared, which is positive 1, because I squared is negative 1. So I get 1 plus 1 is 2. And I just distribute the like terms together. That's not horribly fast, but it's not fantastically slow either. Right? So be careful. I mean, I'm going to give you problems like this on the test. You're going to see at least one of these in the homework. I think they gave you a couple of these.
You did.
Where if I give you a complex answer, its conjugate's got to show up.
This is 3.6, number 40. Find web assignment. I think in there it was like -3 in the book.
Yeah, this is section 3.6, the 35 through 44. That section in 3.6 of the homework. So any other questions from homework? You guys doing alright? Surviving? This is good? Alright, nobody's a zombie. This makes you feel better. I don't survive just that. I watch too many movies. Alright, so there's no other questions. Yes? 3.5, number... 73, okay. Oh, cool. All right. So one reason I assigned this problem is in case I forgot to say this. So very often we use the letter Z to denote complex number. Cool. So it's like the complex variable in a way, right? So we call Z complement. Actually, I say complement, we say that as a conjugate. That represents the conjugate of that complex number. So number 73 says, so we say prove, right? And normally students run the other way when there's a proof problem. I don't blame you too much. You don't get much practice with this. But it says prove that the complement, or the conjugate of Z plus W is that. Now, when you first look at this, you're like, how the hell? So you want me to prove that the big bar becomes two small bars? Like somebody shaved their unibrow. Now it's two separate, like it's supposed to be, right? So you go, my proof is, I just put my thumb there. No, so once you see how to attack these proofs, you'll know how to do all the proofs like this. And a lot of proofs are like this. There's a definition for what Z is. There's a definition for what Z complement is. Conjugate. You with me? So what is this? So give yourself another definition. What would W be? Can't be A plus BI.
C plus DI.
That's crazy. C plus DI. So what's W conjugate?
C minus D.
So wherever you see a Z conjugate, you put that. And wherever you see a W complement, you put that. Now what's Z plus W?
A plus BI plus.
Yeah, so Z plus W is A plus BI plus. Now, collect like terms.
AC plus.
A plus C, that's my real part.
A plus D.
And that's my imaginary part, right? So what must this look like? And your proof would be, you know what this is supposed to look like, because you know what Z plus W is. Now write what Z plus W conjugate is, and show that it equals to what you just got here. So what should this look like, Z plus W complement?
A minus.
Get over it. You do it again, what's the only thing that changes?
A minus.
A minus B. Right?
B minus.
What changes in the
A plus
conjugate?
BI minus.
The only thing that changes is the sign of the imaginary part. So what's the imaginary part?
B plus D.
That. So it's going to be, that stays the same. Minus. So you just got to show that this is that. Because that is this. And then you've proven it. You've proven that this side is this side. Are you guys kind of with me?
Yep.
Shit. So, if I want to prove, in general, if I want to prove that some statement equals some other mathematical statement, I can work with this side until it looks like that side. That'll prove it, won't it?
Yep.
You guys with me? So if I want to prove that 2 is the cube root of 8, I'll work with this side and I get 2. Yay! Now that was easy. Right? So here I want to work with this side, work with it down until I make it look like what that side would look like. And then they must be equal. There's no cheating involved there. I'm trying to make them, if these are equal, then I should be able to write them in the same form. If they're equal to each other, right? If that equals that, I should be able to write them in the exact same form. So that's all I'm going to do. Take this form, write it more explicitly, work with it until it looks like this guy would. Why am I spending so much time on this? Because this is going to be our life for a couple of sections in the trigonometry part of this class. Trigonometry, we're going to be proving trig identities, where we start with whichever side looks easier to start with, and we work with it until it looks like the other side. And if you can't do that, you work with both sides a little bit until they agree somewhere. That is a proof. That is a total proof. If I think this side equals that side, I should be able to get them both to the point where they're in the same form. So that's exactly what we're doing here. Cool. I like it. Maybe. It just takes a little bit of getting used to. This is a really nice way to kind of get your feet wet. Just anytime they introduce another complex variable, give it its own name, like we did with W was C plus DI. So let's try another one of these. What else would they say? So here's how you start to attack this. You realize this side, you start with the conjugate and you square it. This side, you start with z, you square it, and then you take the conjugate of it. So remind me, what's z again?
A plus bi.
So what's z squared?
Fully over.
There are 2 ABI.
Well, let that boy out, right? Can't square the sum. Squares and sums don't play well together because squares are based off of multiplication, not addition. So you got to write it twice. So what's z squared? Good. 2abi plus bi squared. I squared is so minus b squared. So where's that in the problem? It's here, right? Almost. So what do I have to do to actually put something here? What do I have to do to this?
The conjugate.
Yeah, in the conjugate, what's the only thing that changes?
Imaginary.
The imaginary part. Right? What's the only imaginary part in there?
Minus 2.
This guy. So here, I can put a squared minus 2abi minus b squared. That's the conjugate of that. If you like it better, you can kind of collect all your real stuff together. So it's more like a plus bi. So the conjugate would be, leave the real part alone, minus the imaginary part. You guys semi with me. I mean, you can sink your teeth into this now. When you first read through this, I'm sure you're like, how the hell? But you give yourself an expression to work with. That's the most general complex number, a plus bi. There's only one of them in the problem, so I don't have to have one expression. And then I do what the problem says I should do. So in this problem, I'm working with both sides of it. So how would I do this? What's z complement?
A minus bi.
A minus bi. So how do I get this? I just take that z complement, square it.
It's that.
It's that, yeah. So you get a squared minus 2abi plus b squared I squared
Which is
minus b squared, right?
yes.
This would be plus b squared I squared is negative 1. So are these equal?
Mm-hmm.
Yeah. So see, that's the thing. And it feels a little bit like you're cheating sometimes. And I don't know why, but I always get that from students. But I'm just changing the form of this and changing the form of that. And every step I take is completely legal. I'm really just doing what it says to do. So I've made this in the same form as that, so therefore these must be equal. If I can't make this look like that, they can't be equal. There's no way. Yes, sir?
You have to do the normal, the unconjugated z work.
Do you have to?
Do the unconjugated z.
Yes, because what does this tell me to
That
do?
helps you find that.
Take the conjugate of that. So I got to know what that is first. Yeah. Yes, ma'am. Because this is z squared, right? That's z squared. Now what does this side say? Conjugate of z squared. So the conjugate of z squared would have the complex part with a different sign. So one level of this is now understood, hopefully. You give yourself something to work with. They say a complex number squared conjugate equals blah, blah. Well, let me give myself a complex number. Don't give yourself 2 minus 3i. That's way too specific. That doesn't prove anything except for that case. If I say, here is every freaking complex number that ever did or ever will exist. Okay, shit, if you do that, you've proven it for everybody, right? This is every complex number at once. So every complex number squared will look like this. Their conjugate will look like this. And this side ends up being the same. So there, I've proven it. That side does equal that side. Now, in this case, I really got to make this point. If I said solve this, what would you do, of course? Awesome, right? Because it's given to me that it's equal. What am I doing in this case? Can I assume this is true? If I can, then there's no work to do. Awesome. I assume it's true, therefore I don't need to prove it. So let me ask it again. Can I assume this is true? No, because what's the point of this problem? I'm trying to prove this is true. So when you have proof problems, You cannot go adding, squaring, and subtracting stuff to both sides because that's a property of equality. This is going to become even more important when we get to trig stuff. People start doing stuff to both sides. Completely illegal. You don't know it's equal yet, so you can't start throwing stuff around. It's really weird, but it really reinforces why we're able to do what we can do here because it's assumed to be equal. So I'm allowed to do stuff to both sides. If I don't know if it's equal, you can't. You guys are all like, yes. We'll have even more complicated stuff like this? Yes. Okay, all right. I'll do what I can. So you got to just jump into those and try them out. So this is how you start to attack them. And then just bring it up to me if you have any trouble with any of them specifically. So yeah.
Number 7 says there's 2 larger than the conjugate of the conjugate.
I love it. Yeah, so you can have these stacks. They look like pancakes to me. The conjugate of Z. Of course, it's kind of like turn around again. Okay, I'm back. Right, do a 180 again. Okay, I'm back. Yeah, so the conjugate of the complex number is the complex number. Right.
Do you want to do the work?
Yes. You'll do Z complement is A minus BI. So what's Z complement? Change the sign. A plus BI, which is Z. Proven. There's your gimme. Right. It was too easy to even say, what do I show? You show that. You show me what complement is, and then you stack another pancake on top, and you show me what that is. Right? Cool. Enjoy that it's easy. Right? That one barely took any paper space. I like it when students get angry that it's easy. But it's so easy. Holy crap. Let it be easy. It's nice. Okay. Anything else from homework before we jump into 3.7? All right, this is an excellent question. That's a question that if I don't hear it asked, I start to get a little worried that people are not getting there or just saying, screw that section. I don't know what's going on.
Number 15?
50? 50? 15. Oh, yeah, okay. So how do you factor this here? And this one, let me give you a little hint.
Difference in squares.
All right, so it's different squares, but it's also cubes, isn't it?
Yeah.
So the trick with these that are both squares and cubes, because I can break one up into 3 or 6 or 287 parts, whatever the hell the parts I want, one. And this can be broken into 3 or 2 parts. The trick is you look at it as squares first. If you do it as cubes first, you actually end up with something you can't factor directly. But if you do it as squares first, you can go further. It's really weird. So what do I get if I look at this as squares first? And then you got your cubes you can do. You'll have 2 big dudes that will always require quadratic because you can never factor the big dude. I don't know if you remember that. Big dude in cubes, you can never factor him over nice numbers, over whole numbers. It's going to require quadratic to go further. So I get 2 little nice pieces, right? The little dudes will be x minus 1, x plus 1, that's nice. And then these will be big dude squared, so I just use quadratic to get the zeros. Is that cool? Who asked that question? Is that cool? Yeah? Yeah. It's good? Okay. Alright, good. So again, on that section, I would do part B first. I know they asked part A because they actually want you to use synthetic division on this. There's absolutely no reason to do that because that is completely factorable. So why would I do that? If I did synthetic, what would it look like?
1.
Yeah, the only thing I use is 1 or negative 1. And it'd be 1, 0, 0, 0, 0, 0, negative 1. I think, right? 6, 5, 4, 3, 2, 1, constant. Yay, alright. And it would work. I know it would work because that relates to that. But good God, don't do that. Just factor it. It's nice. That section I would just factor first. Okay, good. I can never tell with you guys. Nobody's asking any further questions, but a lot of you have this pained look on your face, like, what? I don't know where to go with that. Okay. So we're going to get into section 3.7. I'm going to talk a little bit about it, and then I'll let you guys work on a handout. And we already talked a little tiny bit about it last time. We talked about vertical asymptotes. I don't know if I actually said the phrase vertical asymptote. We did? Oh, all right, good. Good job, Jeff. All right. So an example, a very simple example, would be that. It's even easier than the one we looked at last time. Vertical asymptotes are walls that I put up that say you cannot go here. This is not a part of your domain. So in this case, of course, what would that vertical asymptote be? Yeah, x can't be 1, so there would be a vertical asymptote at x equal to 1. And remember, x equals something is a vertical line, right? So, word pass. That's the idea of a vertical asymptote. In fact, this guy is kind of simple. He's just, this guy shifted to the right one. So this asymptote here just shifts over to 1 like we know. So that's actually just a shift of a image that we should know. Okay. So let's get into more complicated stuff. Let's talk about, so that's where vertical asymptotes, they come from the domain. So in general, they come from the bottom being set equal to 0. Because that's where I put my wall. The wall says you can't go here. So what about horizontal asymptotes? So this would be the idea of what happens when x gets really, really, really big. So I can have 3 basic situations. I can have, for example, this guy. Let's see if you guys can get this idea. Let me do this completely by the book, and then we'll talk about the shortcut method. All right. So here's how to do this completely by the book. Yeah. So this is all horizontal. Vertical asymptotes come from the domain, what's not allowed to happen. Horizontal asymptotes come from when x gets really, really big, what does that function have to do? Does it have to approach something? That's the idea. So this is letting x go to infinity and negative infinity. So let me do it completely by the book, and then I'll show you the shortcut. We'll talk about the shortcuts. So by the book, horizontal asymptotes. So I want to take this expression, and I'm going to bring in something I think I introduced very briefly before, the symbol for letting x get really big, or letting x do anything specific. It's the limit. So as I let x get really, really big, is there some limit to what x can do? Is there like a maximum it reaches or a minimum it reaches? So you can imagine, think about this guy. A nice easy example. When x gets really freaking big, that's 1 divided by really big, which is
Really close to 0.
really small, right? When I divide 1 over 10,000, 1 over a billion, 1 over a billion to the billion to the billion to the billionth power, to me that's basically freaking 0, right? My calculator would say 0, because you can't go that far out. So this guy, the limit would be 0. There would be an asymptote. In fact, we know what this looks like basically unshifted. It's going to 0 there. And I think I talked about it a little bit at that point. That it's going to 0 as x gets really, really big. As x gets really, really small, it goes to infinity. In this case, it would be as it approaches 1. When I get really close to 1, this thing is going to go 1 divided by really small is really big.
That shifts the other side that way too, right?
Yeah, everything shifts over. Cool. So here's how you kind of do this algebraically, and then we'll do the shortcut. Basically, we'll always do the shortcut. I just want to show you this once. The highest degree is what?
2.
2. So you divide the top and the bottom by x squared. Now, what am I not allowed to divide by? 0. And couldn't x be 0 in general?
Yes.
So why am I allowed to do this? Because, of course, I'm letting x get really freaking big. So I know it's not 0. So that's why it's completely legal. I am so far away from 0, I know that's legal. How we doing so far? You're all like, I wasn't really worried about the joke. All right. So what is x divided by x squared?
X divided by x. 1 over x.
1 over x. And what's 1 divided by x squared? 1 over x squared. What's x squared divided by x squared? 1. What's x divided by x squared? Good. And what's 4 over x squared is 4 over x squared. That's crazy. You with me?
Yeah.
So don't let me not forget my little limit, dude. Alright, so if anybody's going to calculus, I think a lot of you guys were planning on it. Hopefully you still are. If anybody's going to calculus, you're going to be doing, this is basically the first 2 weeks of your calculus class is dealing with limits. Yes, sir?
So why do you divide both top and bottom?
I'll show you. We know the reason I do it is because 1 over x, when x gets really, really big, 1 divided by really, really big goes to 0. Does it ever get to 0?
No.
No, because the only way to make a fraction 0 is if the top is 0, but the top here is always 1. But 1 over 10 trillion is basically freaking 0. It's 0.000 for a long time. Kind of with me? No. You guys, does that make sense by itself?
Yeah.
And we could do a few examples if you did in the calculator. 1 over 10,000. All right, you get 0.0001. And if you do 1 over a billion, you get 0.000001. So that's getting very, very small. And the limit, when I let x get stupid big, the biggest it could possibly be, it's going to go to 0. So now you see the reason I did that. Now I've got a bunch of little expressions that look like this. What's this guy going to do? This piece here is going to go to 0. This piece here is going to go to 0 even faster. Right? 1 over really big squared goes to 0 even faster. And actually, that's exactly how I'd say it. The speed it goes to 0 is higher. 1 is 1. It doesn't care what x does because there's no x there, right? So 1 is 1 forever. This goes to 0. This goes to 0. So I get 0 over 1, which is 0. So that is the complete technical analysis of this expression, letting x get really, really big. Now here's what maybe some of you guys are thinking about. Which one has the higher degree? So which one's going to grow faster? So the bottom is going to grow faster than the top. He can't keep up. The whole thing's going to go to 0. I'm dividing by bigger and bigger and bigger. Whole thing's going to go to 0. So when the bottom degree is higher than the top degree, the limit will be 0. The horizontal asymptote will be y equals 0. So this guy, whatever this guy looks like, he's going to have to, when x gets really, really big, it's going to have to start approaching the x-axis. Yes, sir?
Then to get the vertical, you just...
Good. You try to, and of course I made one that didn't factor, but not nicely. How's that going? You absorb that? So what 2 other cases could there be then? One case is the bottom degree is higher.
Top degree.
Yeah, I'll let that be the third case. So what's the second case then?
Be the same.
Good. That's the most interesting case. Smart dude back there. Let me see that. So again, I'm only going to do this one more time. We'll do it by the book. But you can see, maybe some of you guys can see what's going to happen. Everything that's going to end up with a variable on the bottom is going to go to 0. Because there will be something divided by really big. It's going to go to 0. What's the highest degree?
2.
2. So divide by x squared. So I'll get the limit 3x squared divided by x squared is 3x squared divided by x squared is 3. 4x over x squared, I have an x left on the bottom. Minus 1 over x squared is that. 6x squared divided by x squared is 6. So all I'm doing, if you need to, you can just put everything over x squared. If you need to. That's all we're doing. So here 1x cancels down, so I get minus 2 over x. Here no x is canceled, so I get plus 11 over x squared. And then, yeah, you can see very quickly that all of these go to 0. So I'm left with 1/2. So this guy's going to have an asymptote at y equal to 1/2.
Turn this heat off.
Alright, so very quickly, while that guy's warming up, the last case is seemingly at first is a boring case, but it actually becomes the weirdest case. Of course, the only case I have left is that the top is a higher degree than the bottom. So of course, if the top has a higher degree than the bottom, the whole idea with this is the bottom enough to keep the top in check? So if the bottom is a higher degree than the top, it's like overcompensates. It kills it. It makes it go to 0. It totally kills it. If they're the same degree, they're locked up with each other. So they're going to divide to some number. It's going to come out to some finite number. If the top is a higher degree, then the bottom can't keep up with it. The whole thing's going to just go to infinity. But, so in this case I have this, but it's going to go to infinity in a very specific way. Right, you know.
How specific?
Well, let's find out. Long divide that for me, while this guy warms up.
Really?
Yes, really. Long divide that for me. Really. By the way, did you guys get an email from me about Blackboard? Has anybody tried it yet? Nobody told me anything. Did you try it? Did it work?
Yeah.
Okay, because I've never used Blackboard before.
No, I tried it.
So I just got an email last week that Grossmont signed in for this Smart Thinking online tutoring thing, but it was only available through Blackboard. And I'm like, well, that's evil. They're just forcing everybody on Blackboard. So I had to get my Blackboard set up. I had to call freaking computer people, and I don't like Blackboard. So the only thing I got on Blackboard right now is that. So if you try to log into Blackboard, you should see my course. It should be active now. If you click on it, there should be a link. Is it true when you first click on it, there's a link?
Yeah.
What's it say? You remember? Smart Thinking or Smart Thinking? Good. And I've got the email. I've got the whole sheet of instructions for what to do. A little bit of background for what it is. It's not just for math. It's for sciences and English and some other stuff. Cool. Alright, so what do you guys get?
A number.
You better not get a number because then you did something wrong.
X plus 5 plus 22x minus 10 over
So do it again.
x plus 5 plus 22x minus 10.
So I agree with other people?
Mm,
No, not quite.
Minus,
So.
minus 18. Or,
yeah, minus 18x.
Here?
Yeah.
Okay. So this part, if I let x get really, really big, what's going to happen to this whole thing?
Let's go to 0.
Because the top degree is lower than is lower than the bottom, right? So that's going to go to 0 anyway. So this is going to go to infinity. I think everybody agrees on this piece, right?
Yeah.
It's going to go to infinity, but it's going to do so by following this line, x equals 5. So let's graph this thing and see what the hell that looks like. That seems a little freaky. We'll graph this one first, and then we'll graph that one second, and we'll see this pop out. If you have a calculator, just sit there. Look on with somebody else. Okay. The bottom is not factorable exactly. You could use quadratic formula and get some things. So we will see a couple of vertical asymptotes. But what I really want to focus on right now is this, what's called the slant. Oh crap. So when I do this, I'm in some weird window.
Oh, okay.
On the other piece you can't even see, it's way up somewhere. So there's another piece that we can't see currently. But look at this line here. Let me see if I can't. If I look at the table real quick, and I set it back to normal, it just say it should be something cool at the table. And get a feel for this thing. Yeah, it's up in the 20s. So let me just change, because everybody kind of, you just watch if you want to. But if I look at the table, normally if I can't see something, I'm not sure where it is, I just go to the table and get a feel for where the outputs are. So I'm just barely not able to see this dude. If I make y max 30, I should be able to see the other part of it. There he is. Okay. Now, here's where things get interesting. This is going to negative infinity. So if we all make the same window, it should look like that.
No, mine didn't even look anything like that when you had the standard window.
Alright, so double check your
Mine looks like yours.
x cubed plus x squared minus 1 over x squared minus 4x plus 2. And did you put parentheses around the bottom?
Yeah, but mine does still doesn't look like that. Graph.
It does. Yours is just having a little trouble for some reason at one of the
His looks just like it.
yours is just having some trouble.
So his is having
Just
trouble.
old.
Sometimes,
Well,
yeah. So let me see. Your graphing calculators, when you get to a vertical asymptote, can you imagine that the graphing calculator does it input every real number value of x? Do you think it does that?
No.
No, because then that would it would never get anywhere. Say this thing doesn't work when it's really just thinking. No, it doesn't do that. It does it every such and such step. So when it hits a vertical asymptote, it's going to freak the hell out. It's going to put in a value, it's here, the next value is way down here, and the next value is way up there. Holy shit, it's going to freak out. Because on one side it's doing this, and the other side is doing that. So sometimes, depending on your calculator, just depending on whatever in there, and I don't know why they're always so different, but it'll either try to connect them, so you actually get a straight line going up that shouldn't be there, because it's trying to connect the points. Or if it's got a better processor, if you have a plus, it really shouldn't do that. 84 plus. But if you have a 83 or something, it might freak out. You have a plus and it's still doing that little heartbeat. Neat. So make your window the same as mine. It's still doing. Yeah, it's got a little heartbeat. Oh yeah, and it's got a line in it, see? So I step it out to 30. So that little heartbeat is it's trying to figure out what's going on at that asymptote. All right, so you will have the calculator freaking out at asymptote sometimes. So let that be. So they have like little heartbeat things. How's everybody else is okay?
Yeah.
All right. And you can see mine trying to understand this too. Now, if I put in there, put in y2, put x plus 5. So that's the line it's following. As it goes to infinity, it's following x plus 5. It's getting closer and closer to the line x plus 5. Because when x gets really, really big, this expression becomes that. Because this piece goes to 0. Cool. So it becomes this. So the bigger x gets, the closer your outputs get to this. That, to me, kind of is cool. If I look a little further over in the x-axis, I can see a little better on the other side. Make x max 20. There, it says that turn. Now here comes the x plus 5. Swoosh. Now in the middle, when x is small, it could do whatever the hell it wants to. But when x gets really big, negative or positive, it's got to approach that line. That's what the horizontal asymptote says. It's built on x getting big. So I could even have a function that has an asymptote at 3. So you know at the end it's got to approach it somehow, maybe like that and like this. But in the middle, it could do all kind of weird shit. It could cross it, whatever. So the horizontal asymptote is not as strong of a wall as the vertical one is. The vertical one is, it ain't even in your domain, dude. You cannot come here. Where the horizontal says, when x gets really big, you got to do something. Well, what do I got to do when the x is small? Whatever the hell you want to. I don't care. You can even have a function that's a damped, like when you pluck a guitar string. Thankfully, it eventually goes away, or else every guitar string ever plucked would still be going. That would really be crazy. But it dampens over time, of course, right, because of friction. So this would be what it would. It's approaching that line, but it's actually approaching it kind of like from both sides at once. It's kind of neat. Okay, we'll talk more about this obviously when we get to trig, because this is definitely a trig, a dampened sine function, sine wave, possibly. Okay. Okay, cool. Yes. So, let's do one example together, and then I'll let you guys try out this handout. All we got so far is the theory behind it. We haven't graphed a damn thing yet, really. So let's do an example. Let's see. Well, it's not too evil. Yeah, let's do one like that. Neat. Well, let's do one sort of like that. Let's do this one together. Let's do this first. So, how do I find the intercepts? How do I find the x-intercepts? What do I have to do? What do I want to focus on? No, that would find me the y-intercept. So the y-intercept here would be easy, right? What's the y-intercept going to be? 5. Make x 0, negative 5 or negative 1 is 5. That's pretty nice.
0.
Yeah, to find the x-intercepts, the only way that this could be 0 is if the top is 0. So I want to set the top equal to 0. Don't jump straight to freaking quadratic. You can actually factor this. So 2x and x is, and the only way to factor 5 is 5 and 1, and either the 5 is there or it's there. It actually has to be here because this would make a 10. You can do 10, negative 10, find the factors and make negative 3. Do the grouping thing. That's cool. But when there's only one way to factor these numbers, I would do trial and error. Because there's really only two ways it could be. Right? So to make a negative 3, see here I get a 2x and a 5x. So which one's got to be negative to make negative 3?
The 5.
The 5x, and that's where 5x comes from. Cool. So what are my x-intercepts?
Negative 1 and 5 halves.
Okay. Now, bear with me for a second. Bear with me. I didn't want to do this early. There's a little freaky thing going on here. Let's not do this yet.
Well, the 1 is under.
Calm down. We'll make that a 4. Because do you guys notice, and we might as well talk about this now. If this cancels with the bottom, that's why I don't want to get into this yet, there won't be a vertical asymptote there. Because it does lockstep with the top. There will be a hole there, right? So let's talk about that by itself separately in the next example. Let's make that a 4 there, so you don't have to worry about that yet. So you guys ready? It doesn't change the top?
Yeah.
Okay, cool. I love how you give me no room on me making a problem up out of nowhere. So give me that. Just change it to a 4. Now, how do I find these vertical asymptote? How would I find that?
Base it off of where the bottom can't be 0.
Yeah, so the domain of this guy. So the bottom can't be 0. So of course the bottom factors like
X plus 2, X minus 2.
so that means my vertical asymptotes are going to be at
2 and negative
2 and negative 2. So vertical asymptotes always come from the problems that this guy has with this domain. That's where you got to put the walls up. What situation am I in for the horizontal asymptote?
Where they're the same.
You know what that sign means? It means wait.
You said. I don't know what this means.
This means wait.
Well, now I know what it means.
Universally accepted sign. So you guys, what situation am I in? The same power. So what's going to happen? What's going to be the horizontal asymptote?
1.
Yeah, the ratio of the coefficients of the highest degree. So now we got that shortcut. We don't have to do that limit thing that I did. You don't have to do that division of x squared. When they're the same power, same degree, you just take the ratio of the coefficients. Cool. So this horizontal asymptote is going to be y equals 2. Now notice something very important here. For vertical asymptotes are x equals. Horizontal asymptotes are y equals. So if on a test or a quiz you say horizontal asymptote is 2, you're going to lose some points. It's not 2. It's y equals 2. It's a line. You guys kind of with me? Okay, good, good. I'm just making your day better and better.
Mm-hmm.
You guys can handle it.
So how does that look graphically?
Yeah, so what do we know so far? So now I can put my walls up, right? My vertical walls are going to be at
Negative 2, positive 2.
negative 2 and 2. And let's put our, we're going to have the same kind of problem we did with the graphing of polynomials. I don't know exactly yet what my scale should be for the y-axis. I know that I have a y equals 2 horizontal asymptote. I know I have a y-intercept at 5. But I don't know really what my scale needs to be to capture some stuff. So let's see, for example, I know that my x-intercepts are at negative 1 and 5 halves. Cool. What are the multiplicities of both of those? That never goes away. It's always useful. Don't make it something you got to remember. Make it something that's useful. I have less work involved. The multiplicity of both of these are 1, so they're both odd. So what are they going to do at both of these? Go through. Which makes my job a little easier. I know the y-intercept is here somewhere at 5, wherever 5 ends up when I make my scale. So I'm going to basically come from, it's got to approach that asymptote, go through 5, and then can it turn back?
Mm-hmm.
Why can it not turn back?
Oh, no x-intercept.
There's no door here. So there's a lot of little checks and balances. I know I have to go through. I know I have to go through the y-intercept. The reason it can't turn back is because there's no way through here. And why can't it just go, oh, let's go over there? Because it can't go through the wall. Yeah.
Oh.
So I know it's got to look like this basically. It's almost got a little cubic in there maybe. Right, it's got to go from here through that way. You stop right there. You guys kind of with me? How do I know it didn't start up here? Because where's the y-intercept? At 5. I haven't put it there yet, but it's up here. And what's it got to do at this point?
Go through.
Go through. So I know it's got to start down here, go through. 5 is there somewhere. I just haven't put my scale yet. And where's my horizontal asymptote? It's going to be at 2. So I know over here it's going to look like that somewhat. So let's have a leap of faith here. Yes?
Does the horizontal asymptote go through the middle bit?
Yeah, I put it there, but I know it can cross in the middle. Because the horizontal asymptote only becomes effective when x gets really big. When x is small, it can go through it all day long. Yeah?
Doesn't the y-intercept change to 1.25 because he changed it from 1 to a 4?
So it's 4, 5 or 4.
Oh, yeah, thank you. So that would become 5/4. Thank you. So 5/4 now is 1/4. So that's
I'm talking about the y-intercept.
y-intercept. That's still 5/8. Y-intercept 5/4. Okay, we haven't even figured that out yet. All right. So let's go ahead and make our scale something decent. Let's make it 1, 2, 3, 4, 5. Should be decent. So I know my y-intercept is at 5/4, so that's 1 1/4. I know my horizontal asymptote is at 2. That's not a bad suggestion, actually, that you don't even really draw in the middle, maybe, if you don't want to. So you don't feel like you're supposed to come across it. You can go across it all day long in the middle. On the outside, you got to be approaching it. So I can figure out what f of 1 is, just to get a feel for where this thing is. And what's happening back here?
Nothing.
I really want you guys to be able to kind of imagine what it could look like. It could look like this, or it could look like this. Now, why does it not look like this?
Because it's not
There's
negative.
no door there. There's no x-intercept for it to go through, right? You guys see all the checks and balances here. So once you set up your walls, you put your intercepts on there, it kind of tells you where things have to be. But I'm still going to kind of investigate. Maybe I'm going to figure out what f of 1 is and f of 3, just to see where the hell it is. So what is f of 1? We'll get 2 minus 3 minus 5. 2 minus 3 is negative 6 over negative 3 is 2.
Dang.
Coolness. And then f of 3. F of 3 is 18 minus 9 is 9 minus 5 is 4 over 5, so 4/5. Which doesn't seem right. Did I do that right?
You didn't put negative.
Negative 3, thank you. So negative 3 will be 18 plus 9 is 27. Minus 5 is 22 over 5. It's about 4. A little more than 4. Pop. Okay. So now I know what this thing looks like. I know here it basically looks like that. I could do more points to get it better, but I want to balance between too many points and not enough. So a couple points should be all you need to get a rough sketch. Over here, what's it going to look like? It can't possibly be up here, really.
Well, you did it.
It's got to be down.
Yeah, it's got to be here. And it goes through that intercept, so that makes sense. Right? It goes through both of those intercepts. And then up here, I basically know what it has to look like. It's got to be contained in this little area, so it's roughly like that, approaching that asymptote. So once you set up your walls and you set up your x-intercepts, so I look at those as doors through the x-axis. It kind of tells you where it's got to be everywhere, and maybe there's just a couple points to kind of pinpoint exactly where it is in a certain area. So if you graph this in a graphing calculator, it should look pretty much like this. I know the middle might not be perfectly cubish. Alright, so let me give you this handout. It's got some of the notes on it too, to make it a little easier.
you see